Hello everyone, this is Ankit from KAILASHA Foundation Fun and Learn portal. We'll learn probability today and we'll focus upon this chapter and this lecture is very long lecture as I am planning it right now. And don't worry if there are technical glitches, we will start again. But today this lecture will go at least for a few hours. Okay, so I would like to request you to share the link with your friends so that they also join and they get benefited with this lecture. Okay, let us wait for everyone to join. And if you have any queries, you can write those in the chat section. Okay, so now we start probability. In this chapter, we have many aspects to look after. At first, when we talk about probability, we talk about chance of occurrence of a particular event. So we have to discuss many things, like we have to discuss event, experiment. What is event? What is experiment? What is a trial? What is an outcome? Okay. What are types of events? Many things we have to talk about. So let's start with probability introduction. Probably, the terms probably, in all likelihood, chance, odds in favor, odds against, too familiar nowadays. Odds in favor and odds against, you can see when you are watching cricket matches and you are, for example, you are watching a match of India versus South Africa and you are seeing like odds in favor of India are 3:7. Then you get to know that if 10 matches have been played earlier, then experience says that in 3 matches India has won and 7 matches South Africa has won. Just for an example, I am giving you an example only. So this is what odds in favor means. So we'll learn all these topics: odds in favor, odds against, chance, probability, experiment, event, random experiment, okay, random variable, everything. And they have their origin in a branch of mathematics known as probability and recent time probability. Okay, this is the introduction part. Now let us come to random experiment, because everything starts with experiment. Okay, an experiment, let me describe you. Yeah, I just tossed a coin, or I just did something which has a few possible set of outcomes, just like I appeared in an exam. So the outcomes are that I will pass or I will fail. Or if I talk about many outcomes, then I can pass with distinction, I can top, I can just pass, I can fail, or maybe I get 0 marks, and even I can get negative marks also. So those are many cases. So experiments can have many outcomes. Experiments can have only one outcome. Experiments can have only two outcomes. Experiment is something well defined that you did and you know that these things are possible. Now you have to learn what is the chance of a particular outcome. Okay. So an experiment may be described as a performance that produces certain results. Certain results. The word certain is very certain. You know already that what all can happen. Okay. A random experiment. An experiment is defined to be random if the results of the experiment depend on chance only. That means no one knows what actually will happen. Okay, you have options that either this or this may happen, but you don't exactly know that what which one of those will occur. Okay, for example, if a coin is tossed, you know either head or tail will come, but you are not sure that head will come, or you are not sure that tail will come. Okay, so this is called a random experiment. An experiment is defined to be random if the results of the experiment depend on chance only. Okay. Now, events. At first we talked about experiment, then random experiment, now events. The results or outcomes of a random experiment are known as events. Let me give you a few examples. Experiment. At first, I am giving you example of an experiment. A coin is tossed. Another experiment is two dice are rolled. Another experiment is three coins are tossed. Okay. And events. Head occurs. Head occurs is an event. Okay. Events. Sum is 7. Difference is 3, etc. Okay. Or we can say both numbers are same. These are the events. Events means a particular okay, one coin is tossed, then how can we expect two heads to occur? So this is an impossible event, but it is an event. Okay, this one is an impossible event, but yes, it is an event. Three coins are tossed, so this is the experiment, but what events we can see? Events. First one is at least two tails occur, or we can say at most one head occurs, or we can say exactly two heads occur. So these are the set of events. Okay. Now I am going to describe the difference between an outcome and an event. One die is rolled. That means one, or 2 or 3 or 4 or 5 or 6. These six elementary single occurrences are six outcomes of this experiment. One die is rolled. It is something that we did. It is something that we did. We actually did this. So this is an experiment. And we are expecting these. So these are events. But these are the elementary single outcomes. These are the elementary single occurrences. So we name them as outcomes. These are six outcomes. Yes, these are events also. But when we say odd number occurs, that means either 1 or 3 or 5 occurs. When we say odd number occurs, that means either 1 or 3 or 5. That means this event is a union of this and this. So we cannot call this outcome. It is an event. These are also events. These are outcomes also. Single occurrences are outcomes also, events also, both. Okay. But when we say like this odd number occurs, that means union of two or more outcomes. That is event. That is not an outcome. Okay. Odd number occurs is not an outcome. It is an event. So event is a broader term. Okay. So event and outcome. Now we discuss the similar differences in just like we talked about event versus outcome. Now we will talk about experiment versus trial. A die is rolled. Trial, yes. Experiment, yes. Two dice are rolled. Trial, yes. Experiment, yes. A die is rolled twice. Is rolled twice. That means one small experiment is repeated two times. One small experiment is repeated two times. Trial, no. Experiment, yes. So experiment is a term that is used in broader sense. Okay. An experiment is a union of many trials. Just like an event is a union of many outcomes. Yes, one outcome is also allowed, but in general sense, event is a union of many outcomes. In similar way, an experiment is a union of many trials. Yes, one trial is also allowed, but in general sense, an experiment is a union of many trials. Okay. So experiment versus trial, event versus outcome. Now we'll talk about sample space and set notion. Sample space, sample space. Let us first talk about sample space. So sample space is the set of entire possible outcomes of an experiment. For example, two coins are tossed, then sample space will be head head, head tail, tail head, tail tail. Okay. For example, a coin and a die are tossed, or we can say rolled. Okay. Okay. So S will be 1H, 2H, or we can a coin is written first and thereafter we have die. So first we write head or tail and then we write the number. So H1, H2, H3, H4, H5 and H6. Thereafter T1, T2, T3, T4, T5, T6. These are 12 possible outcomes and the entire set is called sample space. So when we write in these curly brackets, this is called set notion. Okay. A set can be written by an alphabet. An alphabet represents a set. Okay. It uses the equal to symbol. Okay. So we don't have to use arrows or approximately equal to or something like that. We can directly use equal to sign, and then sets are written in these curly brackets, and the elements are separated by commas. These are the observations. These are the observations. Okay. I'm not giving you the definition. Set theory is another chapter, is completely different chapter. Set theory is something else. We just have to use the notion of set theory here, so I am describing you. And now I talk about union and intersection a bit. Union and intersection for your convenience. Union is represented like this, intersection like this. Union means combine, intersection means common. Say A is equal to 1, 2, 3, 4, 5. B is equal to 2, 4, 6, 8, 10. Then we can simply say A union B is equal to, sorry, A union B is equal to, we have to combine these two. So 1, 2, 3, 4, 5. 2 and 4 have already occurred. So now 6, 8, 10. This is a completely new set. This is A union B, both are combined. Now when we write A intersection B, then we just take commons. So commons are 2 and 4 only. So this will be 2 and 4. Okay. So whenever we write sets like this, we always use curly brackets. Remember that. This is union symbol, just like U, and the reverse U is intersection symbol. Union means combine, and intersection means common. Union means you have to combine two or more given sets, and intersection means you have to take commons from the given sets. Okay. So this was the introduction part. Now we know about experiment, we know about trial, we know about event, we know about outcome. Now the events are of two types: simple or elementary, composite or compound. When we talk about elementary, these are outcomes. Elementary events means outcomes, and something larger, something bigger, something broader than that is a compound event. Okay. Now mutually exclusive events or incompatible events. For example, you have rolled a die. Okay. When you roll a die, you either get 1 or 2 or 3 or 4 or 5 or 6. Okay. When you roll a die, you either get 1 or 2 or 3 or 4 or 5 or 6. So let me talk about even numbers and odd numbers. Let's say there's an event A. There's an event A which says odd number occurs. That means either 1 or 3 or 5. And there's another event B which says even number occurs. That means either 2 or 4 or 6. These two things cannot happen simultaneously because only one die is rolled only once. That means any one of the entire set of six outcomes, one, two, three, four, five, six, only one of those will occur. That means either even or odd, but not both, but never both, because an even number is not odd and odd number is not even. These two things cannot happen simultaneously. That means these two events, which two events? Even and odd. These two events are mutually exclusive events, or we can say incompatible events. A set of events A1, A2, A3 is known to be mutually exclusive if not more than one of them can occur simultaneously. That means two or more events cannot occur together. Thus, occurrence of two events simultaneously cannot happen. Exhaustive events. What is exhaustive events? If two or more events are like that, if we combine them, that means if we take union of all those, then the entire sample space is covered, nothing is left. For example, 1 2, 1 or 2 is an event. Okay, 3 or 5 is an event, 4 or 6 is another event. If we combine all these three, then we get 1 to 6. That means entire set of sample space when there is a case of rolling a die. So if these three events are combined, then we get all the set of 1 2 3 4 5 6. That means we get entire sample space. That means these three events are exhaustive. Exhaustive means the entire sample space is exhausted, nothing is left. If we combine the given events, then nothing is left out of the entire sample space. That is exhaustive event. Now we come to equally likely events, or mutually symmetric events, or equiprobable events. So when we talk about equally likely, then all outcomes of classical experiments. What is classical experiment? Classical experiments are rolling a die, tossing a coin, tossing two coins, tossing three coins, rolling two die. Okay, two dice. So these kinds of experiments are classical experiments. When we talk about classical experiments, then all outcomes are equally likely by default. For example, the probability of occurrence of a head and probability of occurrence of a tail, both are equal. Both are equal to 1 by 2. So when the probability of two events associated with the same experiment, remember that two events associated with the same experiment, when the probability of two events associated with the same experiment are equal, then those two events are called equally likely events. Okay, now probability of occurrence of an event PA is actually equal to total number of favorable events by total number of events. Okay, total number of favorable events by number of total events. Number of favorable events by number of total events. That is classical definition of probability. Now we have a few points. Classical definition of probability: it is applicable only when the total number of events is finite. Okay, it is applicable only when the total number of events is finite. Next, it can be used only when the events are equally likely. Classical probability cannot be used otherwise. For example, let me give you a very good example. For example, I'm talking about if what is the probability of it raining today. You will say, sir, there's almost nil probability because it is the month of April, and yes, it can rain today, but there are negligible chances. Okay, so but if we solve this problem by using classical probability, then there are two events. Either it will rain or it will not rain. That means 2 is the count of sample space, and the thing favorable to us that it will rain, so that is 1 by 2, that means 0.5. That means in two such days, one day it will rain. That is not mm, that is not something which convinces us. Okay, because the classical probability which we used in this problem is not applicable. Why not applicable? Because the events are not equally likely. That means the probability of it raining today is very low, and probability of it not raining today is very high. Okay, so these two events are not equally likely, hence the classical probability cannot be used in this problem to determine what is the probability of it raining today. This assumption is made well before the experiment is performed. Whenever we are using classical probability, that means whenever we are using classical probability in problems like a card is drawn out of a deck of well shuffled 52 cards, that means the occurrence of any particular card out of those 52 is equal. The chance of occurrence of any particular card is equal. That means the event of occurrence of any one of those 52 cards is equally likely to all remaining. The definition has only a limited field of application like coin tossing, dice throwing, drawing cards, etc. That's what I said, that the classical definition of probability applies to only these classical experiments. Okay, in connection with classical probability, we may note the following points. That means that is a probability of a particular event lies from 0 to 1. It cannot be less than 0. That means negative chances of occurrence of an event. There is nothing like negative chance. Okay, we cannot go beyond 0. We cannot go negative. Okay, the chance of occurrence of a particular event cannot be negative. The minimum value is 0, that the event will not occur. Now the maximum probability is 1. 1 means 2. 1 means 100%. 1 means 100%. That means the event is sure and it will surely happen. When pa is equal to 0, a is known to be an impossible event. When pa is 0, a is known to be an impossible event. And when pa is equal to 1, a is known to be a sure event. Probability is 0, impossible event. Probability 1, sure event. Yes, this is how we write probability. If a is the name of event, then pa is probability of occurrence of a. If we have to discuss the probability of non-occurrence of a, for example, even number will not occur is our event. Even number will occur was a, then even number will not occur can be written as a dash or ac or a bar. All of these are spelled as a naught. Okay, or we can say not a. So probability of not a has a formula. Probability of not a, p not a, is equal to 1 minus pa. 1 means 100%, so 100% minus the chance of occurrence of a is equal to the chance of non-occurrence of a. When we take it this side, then pa plus pa naught becomes 1. Okay, A coin is tossed three times. A coin is tossed three times. What is the probability of getting two heads? So let us make sample space H H H H H T H T H H T T T H H T H T T T H T T T. What is the probability of getting two heads? Two heads, two heads, two heads. So three cases are of two heads, and the number of all cases is 8. So 3 by 8. At least two heads. Two heads or more than two. Two heads, two heads, two heads, and three heads. Four cases by 8. 4 by 8. Okay. Now, so 3 by 8 and 4 by 8. These are our answers. Now, a die is rolled twice. A die is rolled twice. What is the probability of getting a difference of 2 points? For our convenience, we can, without writing the entire sample space, we know that 1 1, uh, 1 2, 1 3, and so on up to 1 6. In the same way, 2 1 2 2 2 3 2 4 2 5 2 6, then 3 1 3 2, then 4 1 4 2. That means there are 36 elements in the sample space. 36 elements in the sample space. What is the probability of getting a difference of 2 points? Difference of 2 points, that means 1 with 3, okay, 2 with 4, 3 with 1 and 3 with 5, 4 with 2 and 4 with 6, okay, and then 5 with 3, and then 6 with 4. 1 2 3 4 5 6 7 8. 8 by 36, okay, 8 by 36. Let's see what is it written here. In if an experiment results in p outcomes, and if the experiment is repeated q times, then the total number of outcomes is pq. In the present case, since a dice result in 6 outcomes, uh, mm, this there is a misprint here. It is actually p raised to the power q. P raised to the power q. In the present case, since a die results in 6 outcomes, and the die is rolled twice, the total number of outcomes will be 6 square, 6 power 2. That is 36. That's what I have written here, 36. We assume that the dice is unbiased, which ensures that all these 36 elementary events are equally likely. Without assuming these equally likely, we cannot solve this by the classical definition of probability. Now we have to get the favorable number of events. Difference of 2 points: 1 2 3 4 5 6 7 8 cases. Okay, that is 8 by 36. We also calculated this 8 by 36. Now, two dice are thrown simultaneously. Two dice are thrown simultaneously. Find the probability that the sum of points on the two dice would be 7 or more. Two dice are thrown simultaneously. Find the probability that the sum of points on the two dice would be 7 or more. 7 or more. Sum 7. 1 6 2 5 3 4 4 3 5 2 and 6 1. 8. 7 or more means 7 8 9 10 11 12. Okay, two dice are thrown simultaneously. Find the probability that sum of points on the two dice will be 7 or more. So 6 and then 5 and then 4 and then 3 and then 2 and then 1. These are total 21 cases, and the total number of cases is 36, is that we already know. Sorry. So 21 by 36 is our probability, that is 7 by 12. What is the chance of picking a spade or an ace not of spade from a pack of 52 cards? Picking a spade or ace not of spade, a spade or ace not of spade. Spade are 13. Okay, spade are 13 and ace not of spade are 3. Aces are 4, but ace not of spade are 3. So 13 and 3, these are total 16. 16 by 52, because there are 52 cards, so 52 outcomes. 16 by 52 is 4 by 13 is our answer. Find the probability that a 4-digit number comprising the digits 2, 5, 6, and 7, 4-digit number, 4-digit number comprising the digits 2, 5, 6, and 7 would be divisible by 4. Just a minute. There are comments, there are chats from a few students. Ayush says hi. Hi Ayush. Hello Vaishnavi. Hello Nidhi. Theory, yes, you requested theory, and I have just given you details of random experiment, trial, event, outcome, equally likely event, mutually exclusive event, exhaustive events. Okay, so now find the probability that a 4-digit number comprising the digits 2, 5, 6, and 7 would be divisible by 4. To for the number to be divisible by 4, the last two digits must be divisible by 4. Ah, for the number to be divisible by 4, for the number to be divisible by 4, it must be an even number. That means out of 2, 5, 6, and 7, it can end with either 2 or 6. Now, for the number to be divisible by 4, the last two digits must be divisible by 4. So 5 2, yes. 6 2, no. 7 2, yes. Now 5 6, yes. 2 6, no. 7 6, yes. So 5 2, 7 2, 5 6, and 7 6 must be the ending digits. Now the remaining two digits in the first case, 7 and 6, can be placed in two ways. So 2 factorial ways. So this is 2, then again 2, then again 2, and then again 2. There are 8 ways. There are 8 numbers that will be divisible by 4, and the total number of numbers is 4 factorial. 4 factorial is 24. This question requires permutations and combinations. If you don't know permutations and combinations, I'll discuss that as well. Okay, you have to tell me if you don't know permutations and combinations. I'll discuss that as well. So the entire number of possible outcomes is 24. Number of all possible outcomes is 24, and the favorable number of events are 8. Okay, so 8 by 24, that is 1 by 3 is the answer. Let us read the solution. Since there are 4 digits, all distinct, the total number of 4-digit numbers that can be formed without any restriction is 4 factorial, or 4 into 3 into 2 into 1, or 24. Okay, there are 4 digits all distinct, there are 4 digits all distinct, there are 4 digits all are different. Hence the total number of 4-digit numbers without any restriction, okay, is 4 factorial. Now a 4-digit number would be divisible by 4 if the number formed by last two digits is divisible by 4. That is the divisibility rule. Okay, that means the number must end with 52 or 56 or 72 or 76. In all these 4 cases, we have first two digits remaining. In all these 4 cases, we have first two digits remaining, and we have two options every time for all these cases. So 2 plus 2 plus 2 plus 2 is 8. So we have 8 favorable outcomes. Hence, 8 by 24 is 1 by 3. That is our probability. Now, a committee of 7 members is to be formed from a group comprising 8 gentlemen and 5 ladies. So total is 13. So 13C7 is our sample space count. 13C7 is our sample space count. Okay. What is the probability that committee would comprise 2 ladies? 2 ladies means out of 5 ladies we will have two, and since we have to have 7 members exactly, that means two are already there from ladies, that means five will be from gentlemen. Okay, 8C5 into 5C2. 8C5 into 5C2 is our favorable number of events, and 13C7 is total number of events. Okay, 8C5 into 5C2 is our favorable number of events, and 13C7 is our total number of events. Okay, at least 2 ladies. At least 2 ladies, that means 2 ladies or 3 ladies or 4 ladies or 5 ladies. Now the scenario has changed. Now we have 4 different cases: 2 ladies or 3 ladies or 4 ladies or 5 ladies. We have 4 cases, so we have to add these 4 cases. Now we have 5C2 into 8C3, sorry, 8C5, just like we did it here in the first part. Thereafter 5C3, and when there are 3, then 8C4 it will be. Okay, then 5C4, then it will be 8C3. 5C5, then it will be 8C2. So all the cases we have considered now. Now divided by, again, the sample space count, 13C7. 13C7. Okay. A committee of 7 members is to be formed from a group comprising 8 gentlemen and 5 ladies. What is the probability that the committee would comprise at least 2 ladies? We have the answer. This is A part. This is B part. Now, hmm, statistical definition of probability. Let us read that. Owing to the limitations of classical probability, there are cases when we consider the statistical definition of probability based on the concept of relative frequency. This definition of probability was first developed by the British mathematicians in connection with the survival of a group of people. Let us consider a random experiment repeated a very good number of times. A very good number of times. That remember that. For example, if we have tossed a coin only thrice, and we get head 2 times and tail once, then we can give a completely different result, that head is more likely to win than tail. So Sorry for this glitch. We are back now. Tell me if I am audible to you and visible. The screen is visible. If there are any problems, then we will restart it. Is everything clear? Is everything okay? Can you hear me clearly? So, I was talking about statistical definition of probability. Let us consider a random experiment repeated a very good number of times, say n, under an identical set of conditions. That means we haven't changed the conditions. We next assume that an event A occurs fa times. An event A, an event A occurs fa times. Then the limiting value of the ratio fa to n, fa by n, as n tends to infinity. Okay, as n tends to infinity, very good number of times, n tends to infinity. This is something you have to understand. Something which is very large for you must be the number of times the experiment is repeated. For example, tossing the coin 1,000 times is a tedious task, is a very hectic thing for you. That means you can assume, okay, that is like infinity. That is not infinity, but that is like infinity, tends to infinity, you can say. In that situation, if you are given with the task of tossing the coin 1,000 times, then it is very hectic for you, and this is very boring. So it will appear to you, it will seem that it is like infinity. Okay, so probability of a particular event when n is very large, that means when the experiment is repeated a quite good number of times, then if you have got the favorable outcomes fa times, then fa by n is the probability. Okay, that means we have tossed a coin 5,000 times and we have got 2499 heads. Okay, we have tossed a coin 5,000 times and we have got 2499 heads. That means 2499 by 5,000 will be our probability statistically. Statistically, we will have this probability for the occurrence of head. Okay, if we by chance got 2501 heads, then 2501 by 1000 will, for 5,000 will be the probability. Okay, now the following data relate to the distribution of wages of a group of workers. If a worker is selected at random from the entire group of workers, what is the probability that his wage would be less than rupees 50? Less than 50 means there is no worker whose wage is less than 50, because 50 to 60, 60 to 70, 70 to 80, the wages are increasing and the minimum wage is 50. So less than 50 is not a case. That means it is an impossible event. Then probability is 0. Okay, thereafter his wage would be less than 80. Yes, less than 80. We have this 15 and 23 and 36 total, 15 and 23, that is 38, 38 and 36, we have 74. So 74 is favorable number divided by total number is 74 plus 42, 116, and then 17, 133, and then 12, 145, and then 5, 150, 1574 by 150, that is 37 by 75. Okay, so Now his ways would be more than 100. More than 100, we have this 12 and 5, that is 17. 17 by 150. Last one is between 70 and 100. Between 70 and 100, that means 36, 42, 17. So 36 and 42, we have 78, 78 and 17, that is 95. So 95 by 150. Now, operations on event set theoretic approach to probability. Uh, I think there are glitches. I am closing this live session and starting another live session. Okay. I am closing this one live session and starting another live session right now. So you will not lose the track and we will continue the lecture. Okay. And we will keep discussing probability for quite a good time tonight. Okay. So thanks for joining and stay tuned. We are just starting in a few minutes the next lecture. Okay. Thank you.